Hello everyone, welcome to the video for mechanisms for electrophilic aromatic substitutions of benzene. So in this video, we are going to look through the mechanisms for halogenations, nitrations, Friedel-Crafts alkylations, and Friedel-Crafts acylations. The mechanisms of electrophilic aromatic substitutions involve three steps. The first step, formations of electrophile, the electron deficient species. Step number 2, benzene will attack the electrophile. Step number 3, to remove the protons and regenerate aromaticity. This is to reform the aromatic benzene ring. So far, let's look at the reactions of halogenations. Again, this halogenations is under the type of reactions, electrophilic aromatic substitutions. So outline the mechanisms for the reactions given below. So for these reactions, you have benzene, halogens in the presence of Lewis acid, which act as a catalyst. And we substitute one of the hydrogens with the Cl, and there is a side product HCl. So for our step 1, formations of electrophile, remember that electrophile is our Cl2. So the functions of fluid acid is to make this electrophile more electrophilic. So here's your nucleophile, here's your electrophile. So for the first step, you need to draw your Cl structures, the chlorine structures, and the structures of Lewis acid. So coming from where you have the lone pair, which is on your chlorine, one of the chlorine is attacking the center ion. So ion is come from your period 4, which has empty d orbitals, and it can accept a lone pair. And therefore, you are forming a Lewis acid complex. So pay attention to the charges on top of this chlorine, and there's a negative charge on this ion center. So we call this one Lewis acid complex. So this will be your electrophile, and we are going to bring this structure in our step 2. So let's look at the step 2, benzene attack the electrophile. So using the benzene ring, clearly show the double bonds. So alternate double bond, just make sure that the double bond is alternating. And you get the structures of your Lewis acid complex from step 1. So arrow will come up from the any one of this double bond and then attacking the terminal chlorine. So when you make one bond, you need to break one bond, and both of our electron in this bonding will push towards the positively charged chlorine. So you're generating the aranium ion. All right, so looking at the aranium ions over here. So when you open up this double bond, both of these electrons is donated towards this chlorine. All right, don't forget that initially this benzene, each of these carbons has only one hydrogen. So there is a hydrogen over here. We just show all these 4 bonding. So when you create this carbon Cl bond, the neighboring carbon now left with an empty space. So we put a positive charge on top of this neighbor carbon. All right, so once you form the first aranium ion, we are going to construct the resonance structures. So why there is resonance structures formed for this aranium ion is because the pi bond within this benzene ring, this aranium ion, they are able to delocalize around. That means they are able to move around this 6 carbon. So let's look at the first double bond next to this carboxyl ion. So we are going to move this double bond into the neighbor bonding, which is close to this positive charge. So now the double bond moved towards this carbon, and then originally you have one bonding over here, so the positive charge now fall into your carbon 4. Okay, if I say this one is my carbon 1, this is carbon 2, so when you move around this double bond, now this positive charge fall onto carbon number 4. So we do another resonance structures here by moving another double bond into the center bonding. So move around these double bonds again. And now I have my third resonance structure. So this double bond doesn't change, and then I move around the positive charge. Now it fall onto another carbon. Okay, which doesn't have the double bond. So you can see here, this carbon doesn't have any double bond, so it has a positive charge here. All right, and the second structure here for this carbon, it doesn't have any double bond, so positive charge on carbon 4 and a positive charge at carbon 6. So 3 of these structures are the resonance structures for aranium ion. and you must draw all of this, including the bracket and the double-headed arrow, resonance arrow. And don't forget that after this FeCl3 accepting one chlorine, you have the side products FeCl4 minus. Okay, that negative charge fall on the center ion. So for your step number 3, remove the proton and regenerate the benzene ring. So taking one of the structures over here, clearly show where is your positive charge, and we are going to use this structures, your FeCl4. So in full structures, Fe with another 3 chlorine and 1 chlorine, you need to show the bonding and the lone pair. Don't forget that there is a negative charge on this ion center. So to regenerate the benzene ring, first we use the bonding. We want to break this bond so that we can regenerate the Lewis acid. So both of the electron from this bonding pushing towards the chlorine. And then taking one of the lone pair, you're going to get the hydrogens. So when you make one bond, you are going to break this CH bond. So from this CH bond, all right, from the middle of the bonds fall onto the center so that we can regenerate that double bond in the benzene. So here you go, you have your final structures, a monosubstituted benzene, chlorobenzene. And also, you are generating the side product HCl and the Lewis acid, FeCl3. Alright, so for the next reactions, we have nitrations. In the questions, benzene will undergo electrophilic aromatic substitutions with nitric acid HNO3 in the presence of sulfuric acid H2SO4. Show the mechanism for these reactions. So of course you need to have the reactions equation first before the mechanism. So benzene, when you react with nitric acid in the presence of sulfuric acid under 50 to 55 degrees Celsius, we are going to form nitrobenzene and the side product H2O. So for the first step, formations of electrophile, you need to show the structures of the nitric acid HO and O2 and the structures of sulfuric acid HO, SO3H. Alright, so this is the structures for nitric acid. This is the structures for sulfuric acid. So we're starting from the nitric acid, taking the lone pair from the oxygens, and it's going to get one of the hydrogens in the sulfuric acid. So when you make one bond, you're going to break one bond, pushing both of the electrons onto these oxygens. And we are forming a protonated species. So remember that when oxygens with 3 bonding, there's a positive charge over here. And the structures of the oxo. Alright, or you may write this one as HSO4 minus. So after these structures, you can see there is a structures of H2O. We are going to break this bond between the H2O and the NO2. So pushing both of the electrons towards the positively charged oxygens. And now you remove a molecule of water and create your electrophile. NO2 positive. The positive sign will be located on these nitrogens. So we are going to take the double bond from your benzene. Any of the double bond will do, and then it's attacked directly on these nitrogens. And it's going to form uranium ions. So again, you need to show where's your positive charge. In this case, it's located at the second carbon. And then when you move around the electrons, and now you are creating this double bond along this line. And the positive charge fall onto carbon number 4. And then when you rotate again, you will see the movement of the double bonds to the next bonding. And here you go, you have another double bonds over here and positive sign at carbon number 6. So this is 3 of the structures of your resonance structures of uranium ion. You have to draw 3 of them. So next we have the final steps over here, which is to remove the proton and regenerate your benzene ring. So take one of the structures over here and then imitate the HSO4 negative or the structures of the negative OSO3. This negative is you are going to get the hydrogens. So when you make one bond, we are going to break the CH bond and regenerate your double bond in the benzene. And here you go. You have your final product, nitrobenzenes, and regenerate your sulfuric acid here. So next we have our Friedel-Crafts alkylations. Please learn about the spellings. So for Friedel-Crafts alkylations, it may involve rearrangement. Either is 1,2-hydride shift or 1,2-methanide shift. So if your neighbor carbon has hydrogens, we will first go with 1,2-hydride shift. This is our priority. If no hydrogens present, then only you go with 1,2-methanide shift. So this is to form a more stable carbocation, which will then leads to the formations of your major product. So the stability of carbocation, tertiary carbocation is the most stable, followed by secondary, primary, and methyl carbocation is the least stable. So complete the following equations and draw the mechanisms for the reactions. So in this case, we have the benzene. We have an haloalkane in the presence of Lewis acid. So for these structures, you need to understand that where is the positions of this CCl bond. So if you can't see it from these condensed structures, you may open up this CCl bond. So we are going to break the bonds over here and then substitute with hydrogens in the benzene. So hydrogens and the chlorines is going to form the side products, and where you break the bond is where you're going to attach back the bonding. So the products form is an alkyl benzene. Okay, here is where you break the bond and you combine it back over here, and the side product HCl. So for these structures, we have a name sec-butyl benzene. Sec-butyl benzene. As the carbon attached to the benzene is secondary carbon, and you have 4 carbon in the substituents. Next, let's look at the mechanism for these Friedel-Crafts alkylations. For step 1, we have the formations of electrophile. So you have the structures of haloalkane and the Lewis structures. So from here, we take the lone pair of our halogen, the chlorine, and then it will attack the center aluminium. As aluminium obey the incomplete octet, therefore it is able to accept a pair of electrons. Or in other words, we can say this center aluminium is electron deficient. So it's going to form an Lewis acid complex. But over here, if you realize, the carbon which connect to the Cl is a secondary carbon. So we can break out this bonding straight away. Okay, we can open up this bonding. So the pair of electrons from this bonding push towards the positively charged chlorine. And we're going to produce a secondary carbocation. Okay, so secondary carbocation is a little bit more stable, so it can stand alone. Okay, you can produce a secondary carbocation. And then plus a side products over here, AlCl4 negative. So I'm just showing the bondings over here, or you may write as AlCl4 negative. So the next steps, we have the benzene attack the electrophile. So using a benzene and the electrophile we create in step 1. So from the double bond, any of the double bond will do, and then it will attack the positively charged carbon, and it's going to produce 3 resonance structures of uranium ion. So there is a positive charge on the second carbon, and then you need to draw the arrows to show the delocalizations of the pi electrons. Alright, so from the double bond, push into the center bonding next to it. And then now you are having the double bonds over here. And then initially there is double bond here, it doesn't change. So the positive charge now fall onto carbon number 4. And then next we take another double bond and then push into the middle of the bonding. You have your double bond over here and the positive charge at carbon number 6. And then the last step to reform the benzene ring. So taking one of the structures from your uranium ion, and then please remember to show this positive charge and the hydrogens. So taking the AlCl4 negative, we will start from the bonding between aluminium and chlorine. When you push into the chlorine, taking one of the lone pair, and it's going to grab these hydrogens. So when you make one bond, we are going to break this CH bond and reform your aromatic ring. There is your product, sec-butyl benzene. And also you have the side product HCl, and the Lewis acid is regenerated. Alright, so next we have Friedel-Crafts acylations. There is the reactions between a benzene and an acyl chloride. Okay, this is the structures of acyl chlorides. So for this acylations, again the same thing, you're going to replace one of the hydrogens in our benzene with the acyl group. So imagine that we take out the hydrogens and the chlorine from the acyl groups, and then you're producing the side product HCl. Alright, so where you break the bond is where you form the bond. So we're breaking the bond between carbon hydrogens here and between the carbon Cl over here. So here is the new bonding formed between the benzene and the acyl groups. So the structures have a name of acetone phenol. Alright, so next in the mechanism, first step, formations of electrophile. So using the acyl chloride and the Lewis structure and the Lewis acid, take the lone pair from your chlorine, attack the electron deficient aluminum, and you're creating the complex like this. So we want to break out this carbon chlorine bond by using the lone pair from your oxygen. So pushing the electron into the double bond, and you are going to push away these two electrons towards the positively charged chlorine. And now we are creating the acylation ion. So in your acylation ion, there's two resonance structures. So when you push in the lone pair into the double bond, you're creating triple bond. And when you break out, so chlorine will attach with this chlorine as your leaving group. So you're going to form this Cl, AlCl3 with a negative charge on this aluminum. So to form another resonance structures, you will push away this pair of electrons back to the positively charged oxygens. So both of this acylation ion, you can swap the positions, doesn't matter. But take note that we are going to form the bonding with the positively charged carbon for the second structures here. So in the steps 2, using the benzene and one of the acylation ion, so we're taking one of the double bond, doesn't matter which one you're taking, okay, it's attacking the carbon which bearing the positive charge, and you are forming the resonance structures of aromatic ion. You may also want to draw this arrow from the double bonds over here, doesn't matter as long as you shows the correct resonance structures. So the formations of the resonance structures of uranium ion is repeating. Okay, so resonance structures, you can refer back to the previous reactions. And the next step, to regenerate aromatic ring, also the same thing. Taking one of your uranium ions and then you use the AlCl3 forming from your step 1. Okay, so from the middle of the bond, pushing into the chlorine, taking one of the lone pair, get the hydrogens, break the CH bond, and regenerate the double bond here. And we are forming the acetone phenol, side product HCl, and Lewis acid AlCl3. Right, so revise back the mechanism for these 4 reactions for electrophilic aromatic substitutions. They all involving 3 steps. Formations of electrophiles are different for all these 4 reactions, but for second step and the third step, they are kind of similar, in which step 2, we are forming the uranium ion, and you need to show the 3 resonance structures. And then step number 3 is to reform the benzene ring in your product. Right, so please practice again for your mechanisms, and you can try the exercise in chapter 6.3. Thank you, and I'll see you in the next video.